Okay, we have one participant. We have two. Okay, we have three. Okay, let's wait one more minute. We have already a reasonable number of participants. Okay, there is not much movement now, so maybe we should start. Okay, so good afternoon, everyone. Welcome to this NITheP webinar. Today's speaker is Dr. Garry Kemp from the University of Johannesburg. Garry is a theoretical physicist by heart, but he is employed in a mathematics department at the University of Johannesburg. He did his PhD with Robert de Mello Koch at WITS. And since a year or a little bit longer, some of us, in fact, all of us on the panel, have been working with Garry on a topic that is close to our hearts, which are open quantum walks. And Garry developed the theory of the lazy open quantum walks, which is a property of the walks and not of the speaker. Yeah. So, Garry, we are very happy that you are with us this afternoon, and we are very much looking forward to your presentation. So, Garry, please, over to you. You're welcome to share the screen again.
Thank you very much. I need to find it again. There we go.
Yeah.
Okay, so hopefully you can all see that.
Perfect, thank you.
I'm also just going to stop my video. And okay, so yeah, hopefully you can hear me and see the screen, see the slide. So thank you to Francesco and Ilya for the nice invitation to give a talk. Yeah, so the title is Lazy Open Quantum Walks, and it is based on a paper that we have written. That's the archive number at present. And yeah, so this is also in collaboration with Ilya and Francesco. So good. Start off with an introduction. So random walks are found in many fields in physics, for example, and computer science. They're fairly ubiquitous things. Even financial mathematics and I guess some biological models also make use of random walks. So they're quite a common thing. Now, random walks were upgraded to the quantum level by many papers. I've listed some over here. So a list of researchers that have done this, people like Aronov et al. In '93, so it's the early '90s, Fari in '98, Kemper in 2003, and I think this article here is quite a nice review paper on various models that have been constructed throughout the years. So typically, what can be done, or what is done in some of these models, is that they construct unitary models, right? So basically, you have a state of the walker that's given as this expression here, this tensor product. So this state I over here, that's an element of Hilbert space. And this state over here, it basically labels the position on some underlying graph or some lattice, right? So the graph on which the walker is moving from site to site. Okay, so that's just some orthonormal basis labeling those positions. Then in this state, this alpha, that is a state that is describing some internal degree of freedom, right? So Examples that are often given are this could represent spin or polarization, something like that. All right, so that's also an element of another Hilbert space, which is sometimes referred to as the coin space. Right? Yeah, so that's how you describe the state of the walker. It is then typically what can be done, it is then subjected to unitary evolution. So this is a closed system and the dynamics is unitary. So the unitary operator can look something like this. Again, it's a tensor product. Now, this C operator here, this matrix, this guy is going to act on the alpha state. And that's going to be responsible for transforming the internal degree of freedom, right? So, yeah, so it's a transformation, and it's affecting the internal degree of freedom, right? Then this S operator, this is sometimes referred to as the shift operator, that is acting on the state I over here, and that's going to be responsible for shifting or changing the position of the walker, either moving it left or right or whatever, right? It is in charge of the actual movement on the graph, okay? And then, yeah, so continuous application or successive application of this unitary operator on the state then generates nice quantum correlations between the different positions, right? And what can happen if you maybe choose your coin operator, for example, in a nice way, the interference effects that can lead to really different behavior, different or interesting behavior. So what I've got here, so just some nice pictures, some illustrations. So on the left-hand side, these left-hand side pictures, so this shows at the top here, for example, this shows the probability distribution for a particular unitary model. So this model over here, so this was just a one-dimensional walk. It was a two-level system, so maybe you can think spin up and spin down. So the coin space, I think, is just C2, right? The initial state was at the origin, and I think the initial state of the internal degree of freedom was just a superposition between spin up and spin down. And then you apply this unitary operator, thinking after maybe 100 steps, this is the probability distribution that you can plot or that you get. And just comparing that on the right-hand side with the distribution that's on the right-hand side. So this is just a very simple, symmetric, random walk, equal probability to go left, equal probability to go right. And I think also something like after 100 steps, you can plot the distribution. So the right-hand side, what I'll refer to as the classical random walk, it looks very Gaussian. Most of the time you'll find the walker at the origin. So that's how that is working. And almost, kind of the opposite situation of what's happening here on the left-hand side. So the two distributions look very different, right? Oh, and the coin operator in this case was the Hadamard matrix, right? So just this 2x2 Hadamard matrix. And even if you plot the variance, right, this sigma squared parameter, for the unitary quantum random walk, it looks nice and quadratic. And you contrast that with what's happening in the classical case. So this variance, this behavior with time, or with this parameter n, it looks very linear, right? So this is just a simple illustration just to show that thinking of unitary quantum random walk models can be very interesting, and it can lead to different behavior from the classical case. So good. Now, the example that I just showed, that was for a non-lazy walker, right? So by non-lazy, I just mean that every time the unitary is applied, there is no possibility of the walker staying put, right? There's no chance of the walker remaining on its site. So it has to move to a different position on the graph, okay? Now, lazy unitary random walk models, they have been formulated, and I've cited some interesting papers of people that have worked on this. So there's Childs in 2010, there's Wong in 2015, and other papers that follow. And I guess the main thing that I'd like to get across in this slide is that there are some interesting things that can be learned by considering lazy walks, right? So, for example, in this paper, this 2015 paper here, so one application could be in terms of search algorithms. So what's happening in this paper here, so the author claims, at least, to have formulated Grover's search algorithm as a lazy unitary quantum random walk. And the interesting thing here was that, or the interesting that was claimed to have been discovered, was that adding additional self loops to the problem, to the model. Basically, so what that means is, adding self loops just in that paper just means increasing the probability of the walkers staying on the same site, right? So what was found was that adding additional self loops can actually affect the performance of the search algorithm, right? So it was found that one self loop increased the success probability of the algorithm, but adding more than one self loop, so basically increasing the probability of increasing the laziness of the walker, actually supposedly led to a decrease in the success probability. So I thought that was quite an interesting thing. Maybe one more effect that I'll just maybe mention is something called localization. So so depending on the unitary evolution operator, right? So that unitary matrix, depending on what its eigenvalue spectrum looks like, the walker can actually exhibit a non-vanishing probability to remain at any position on the graph, right? So that's also sort of described in some of these papers here. So I thought that was interesting and something not necessarily intuitive or something at least worth noting. But again, the main point I want to get across in this slide is that it is possible, and there are reasons for actually studying now lazy walks, right? Even if it's just in the unitary case. Now, unitary. So that was the unitary case. All dynamics there was a closed quantum system, and the dynamics was unitary. Now, in some really nice papers by Francesco and Ilya, and some friends in France, some open quantum walk models have been formulated, right? So what's happening here is you have a system, right? And it's comprised of the walker, again, possessing some kind of internal degree of freedom, as well as the underlying graph, right? Or the underlying lattice, whatever you want to describe it to be. Right, so that's going to be the system. It's the walker with the internal degree of freedom and the underlying graph, and the evolution is driven by some kind of dissipative environment. Okay, so some kind of interaction with an environment. That's what's driving the movement on the graph. The state of the system, right? The state of the walker is now some kind of density matrix, and it's an element of this space. So it's an element of the space of operators that act on this Hilbert space H tensor K. All right, and I think now I mean this space K that is describing the positions on the underlying graph. And this Hilbert space H, that is the space describing the internal degree of freedom of the walker. Okay, so then what can be done is you can define generalized quantum coin operators, right? So this Bij, right? So these quantum coin operators are describing the dissipative interaction between, for example, nodes I and J, right? So so my understanding is of what's happening here is that between any two nodes on the graph, say maybe node I and site J, or node I and node J, there's an interaction between the system and the environment. Okay, and that's what's sort of facilitating the jump, right? So this quantum coin operator, this is describing a jump from site J to site I. Okay, we insist that these operators satisfies a normalization condition. So summing over this index I over here for this expression, the B dagger B, that must give you the identity matrix. So that's a normalization condition. And then for every site J on the graph, we can define this completely positive trace preserving map. And I think this is also, some people refer to this as the Krauss representation. Okay, so it's just a sum over I, and you've got the first quantum coin operator acting on tau. So tau is the state describing the internal degree of freedom, and then you've got your B dagger. All right, so that's at least the map that's happening on just this space H, right? Now we can extend the map to act on the full Hilbert space, right? Because now we also want to describe the actual movement on the graph, right? Not just the transformation of the internal degree of freedom. So now we define these MIJs, right? To sort of, in this, given by this expression, in this tensor product. So this outer product here, right? This IJ, this is now describing a situation where the walker moves from site J to site I. Okay, so we've extended the map to be acting on the full Hilbert space now. And again, we insist, we require this normalization condition there, right? So now the map on the full space, the full map acting on the density matrix rho is given by this expression, right? We sum over I, we sum over J, Mij rho, Mij dagger, right? So here we really are thinking about a discrete time open quantum walk, right, on a graph. Now, as far as the initial state is concerned, we can restrict our attention. To this form over here for an initial state, right? So this is some sort of statistical mixture between the different positions on the graph. And you'll notice here that there's no mixing, right, between the different positions on the graph, right? So yeah, there's just no mixing. You can, if you wanted to, choose an initial state where there is, for example, some mixing going on. So for example, you can also sum over some index J. This can be tau ij, and this vector here can be I, and that one there can be J, right? So you're sort of highly mixed initial states. But what you'll find is that after a single application of the open quantum walk map, right? So after a single application of this M, all of that mixing goes away, right? So all of that mixing goes away, and yeah, so, you know, at the end of the day, you'll get some kind of expression that looks like that, right? So for all intents and purposes, we can really restrict our attention to a density matrix that's given by this expression. So at some random time n, for example, at some given time, the state of the system, right, could look like this, could be given by this expression. Again, you have a sum over I, this matrix over here, this tau in, that's a matrix describing the internal degree of freedom. And of course, this outer product, that's describing the position of the walker on the graph. This expression here, right, or this matrix is given by this sum over here. So yeah, basically when you think of applying this map, you can do so inductively, you know, so for any time n, you have these two expressions here. So that's the general form of the state at time n. So if you want the probability, right, so the probability, for example, at time n to find the walker at position I, right, so I is some position labeling some position on the graph. Basically what you can do to get that probability, you take the trace of this matrix here, right? So at time n, the probability to find location x equal to I, right, would just be the trace of this matrix. Okay, so that's what's happening there. And then I've added in a nice picture just to maybe further illustrate what's going on. So I've drawn here a bunch of nodes. I've labeled nodes I, J, and K. And I've just basically put in the these coin operators just to indicate, the directions, which way can jump to which one. So, for example, if the walker is at side K, then moving to side I, that's described by this coin operator BIK, right? So that's describing the transition from K to I, right? And of course, I've added in these self loops here. So BII, that just describes a situation where the walker starts at node I, and then you apply the map, and then it doesn't go anywhere, right? So it stays at site I. So yeah, hopefully this illustration helps a little bit. Now, it should be said that there are many interesting things that can be discussed and that have been shown about these open quantum walks. And they can be found and read about in the nice papers by Ilya and Francesco. But most importantly for us in this talk is that there has been shown, or there's been proved or derived, a central limit theorem, right, for non-lazy open quantum walks. And that was done by one of their collaborators, this Attal et al. In 2011. So basically what they do is they prove a central limit theorem for something called a homogeneous open quantum walk on a d-dimensional lattice, so this ZD, with the assumption of a unique steady state, right? So that's sort of, that'll be important for us in this talk. And then in 2015, again, Ilya and Francesco, what they did in that paper is that they achieved a microscopic derivation of these open quantum walks, right? So they derived these OQWs from a microscopic model. So basically, what they did is they wrote down a total Hamiltonian to describe, everything that's going on. This HS, that's the Hamiltonian for the system. So again, that's the walker and the lattice. The walker, along with its, describing its internal degree of freedom. This HB, that's the Hamiltonian describing the environment, which concretely in that work was taken to be a bath of harmonic oscillators. And then this Hamiltonian describing the interaction between the system and the bath, right? So then what they do is they study the resulting reduced master equation, and they do some sort of time discretization of that equation, of the differential equation, to eventually, at the end of the day, obtain our OQW formalism, right? But crucially, what I guess crucially for us, or the take-home message of this slide, is that in this microscopic derivation paper, they show that any microscopically derived open quantum walk must be lazy, right? So it must have the option to not go anywhere, right? So with that insight, okay, with that in mind, we now think of this work here, the central limit theorem work, and this poses an interesting question. So if we were to formulate a lazy open quantum walk, do we still have a central limit theorem? Or at least, what does it look like? Does it change in some way? Basis of this calculation, of this work, right? So that's the interesting question, which I will now attempt to answer. So to then proceed, again, let's consider a homogeneous, what's called a homogeneous discrete time open quantum walk on a d-dimensional lattice. So we have this the space ZD over here, and we find it useful to introduce or bring into the game this canonical basis, right? So these set of unit vectors, the E1, E2 up to ED, and we identify this ED plus J as minus EJ, right? So these unit vectors are basically describing the different the different directions that we could walk on this lattice, right? So this E1, for example, that is describing basically movement along that particular axis, right, in the positive direction, right? So you have this axis, and its unit vector corresponds to E1, and so just this E1 here describes a movement along the positive direction, right? But the walker could also go in the negative direction, right, of that corresponding axis. So that's what this vector is now describing, right? So basically putting all these together, for each site on the lattice, there are 2D adjacent sites, right? So 2D different directions that the walker could go in, right? So, both on the positive direction, right? And also along the negative direction. And then to try and encode the idea that our walker is lazy, we also include this, this little zero vector here. So we just define E0 to be 0. We include that in our formulation. So now putting this all together, there are 2D plus 1 possible things that our walker can do, right? So it can move in any direction. So that's 2D options for it to do. And it can also stay put, right? It can also not do any, it reserves the right to not go anywhere, right? So that's the 2D plus 1 possible jumps, possible options. We also have the coin operators, right, that we want to define. So this is now given by these A's, right? So the B's in the sort of the general formalism that I described a few slides ago. This is now, those B's become these A operators, right? And basically what I mean by this term homogeneous, in my understanding, is that if the walker wants to go in the positive direction indicated by E1, right? So along that axis, no matter where the walker is on the graph, you're always going to use this A1 operator, right? So this A1 is constant no matter where the walker is on the graph, no matter what site, right, on the lattice. If it wants to move in that direction, you're always going to describe that with A1. And, same thing can be said about all these other operators, right? A2 and so on and so on. And this A0 over here, that encodes the idea that our walker is now lazy, right? So good. So like we did with the B's, we need to impose the normalization condition for the A's, right? So we sum from J to 0, or from J from 0 up to 2D of A dagger J AJ, and that must be the identity matrix, right? So this is our normalization condition. So in this slide, I'm just explaining what the map, the OQW map would look like on the lattice. So if I want to just transform the internal degree of freedom, this is what the map looks like. Okay, so tau is an element of that Hilbert space. So that's good. If I wanted to expand or extend the map to act on the full Hilbert space, right? So also now convey the idea that the walker is moving on the lattice, I now define these MJIs, or these MIJs, as this tensor product, right? So there's this expression. So in this outer product, this is telling us, okay, so the walker is at this position labeled by this index I, right? So that's where it is. And it then would move in the jth direction, right? So J is the index, it goes from 0 up to 2D. So that's what this operator is basically describing. It starts at I and it moves in the jth direction, okay? And so the general map or the map on the full state would look like this, right? So we sum over I. I is its position on the lattice. J is an index that labels the different directions it could go. And that's what the expression looks like. Okay, and then similarly at some time n, we can think of them as the state looking like this, as this sum. Again, no mixing between the different positions. You apply the map M once, and this is what the state then becomes, right? And this tau is given by that sum over there, right? So this is just the map on this d-dimensional lattice, right? And if that wasn't clear enough, here's another picture. So this is just an illustration of a two-dimensional lattice. And I think on this picture, the positive direction, I guess it ultimately doesn't matter too much, but at least in my mind, I have the positive, one positive direction as going from the bottom left to the top right. Okay, so that's the one positive direction, and movements in that direction is described by this operator A1. Okay, and then movement in the negative direction, right, in the negative direction along that particular axis is described by A3, right? And then the other positive direction that at least I've thought about is going from the top left to the bottom right. Okay, so top left to bottom right, and movement in that positive direction, that's described by A2. Okay, and then in the opposite direction, that's described by A4, and I also have the necessary self loops. Okay, so just a picture to try and understand what it was that I was talking about. Okay, so let's just have a look at a very simple example, right? So just a one-dimensional example. I wrote down three operators, an A1, A0, A2. They satisfy our normalization condition. Again, just a little illustration of what's happening. So A1, that's the operator that describes movement to the right. A2 describes movement to the left, and we've got the self loops. The initial state I've chosen to be this form over here. So that is the half of the identity matrix. That's that's the internal degree of freedom part of the state, and the walker is starting from the origin. Okay, so if you apply our CPTP map a bunch of times and then calculate the probability, right? So again, remember the probability. To calculate that, we take the trace of that tau matrix, right? So if we go back to figure out what the probability is, we're taking the trace of this expression here, right? So good. Now we get pictures, we get plots that look like this. So this top left picture, so this is what happens, I think after 10 steps. Okay, so this is what the distribution looks like. You get a bunch of points. After 30 steps, the distribution looks like this. So by now it's starting to take shape. 60 steps is this bottom left picture. And after 100 steps, it's this picture here on the bottom right. Okay, so it looks very nice and Gaussian, and just a simple example just to show or illustrate how these OQWs are working. Okay, now we discuss quantum trajectories. So the trajectories, or these quantum trajectories, this is a nice way to simulate the open quantum walk as a classical process. So what is happening here at some time t, right? So t equal to n, so at some time n, you can think of maybe the initial state or the state at time n described by this. So we have a tensor product, there's tau n, and this outer product there. So do this index in, that's labeling the position of the walker on the graph, right? Now, what happens is you apply the map M, right, the CPTP map, you apply it once, right, to your state over here, this row N, and then immediately afterwards, you perform a measurement of the position, right? So then what happens is that the state jumps to a new state. So at time n+1, after the application of M and after the measurement, the state ends up looking like this, right? So the internal degree of freedom, that matrix has been transformed in this way. The state describing the position now looks something like that. And of course, I need to renormalize the whole thing by dividing by the probability, right? So the trace of the new state is 1. And again, you know, this P, this probability, again, that's just the trace of this B tau B dagger, right? Now, by repeating this process over and over again, you know, applying the map, doing a position measurement, then applying the map again, doing a position measurement, what this gives us is a Markov chain, right? With these events over here. So this tau n and this xn, and again, this tau n for the internal degree of freedom, and this xn describing the position on the graph, right? So now this is giving us a Markov chain. Now, what do I mean by the simulation, right? So how do we simulate this open quantum walk with these quantum trajectories? So at least, yeah, what you can show is that the expectation value of the n+1th state, given knowledge of the nth state, right? So this expectation value here is nothing but, or the same as applying the map, the open quantum walk map, to row n, right? So that's, yeah, that's a nice little thing to, know. But yeah, essentially what we have in this slide, you know, so what we gain from this knowledge is that this quantum trajectory framework, you know, through this, we now have a Markov chain, right? And this Markov chain, it's susceptible to, you know, standard analysis of, you know, probability theory, and we can apply theorems that one would normally, you know, apply in probability theory, and so on and so on. All right, so we now have a Markov chain. So good. So what does the quantum trajectory formalism look like for our lattice, right? Because we want to, you know, we want to consider a homogeneous open quantum walk just on a d-dimensional lattice, and this is what we have over here. So, you know, this expression, again, that's internal degree of freedom state, and this x of n+1, that's describing the position. Again, after you apply the map and you perform a position measurement. Okay, and again, this probability, that's just the same expression, it's the trace of that expression, right? And then also a key ingredient for what we're going to do. Now, it can be shown, or it can be proved, at least in this paper over here, very nice paper by Krummerer and Marson, 2004. So you can show that this time average, right? So this sequence over here, it converges almost surely to a random steady state row. Okay, so yeah, that's argued in that paper there, and we're going to make use of that. And an additional assumption I would say is that our steady state is unique, right? So armed with all of that, we can start to address the issue. So we start with these independent and identically distributed random variables, which are these unit vectors, the e's over here. We define this quantity m, so that's just the expectation value, right? And you know, expectation value is just it's a weighted sum over these e's, right? These unit vectors. And you know, these weights is nothing but the probabilities, and the probability, you know, this is given by the trace again of these coin operators, but now we're taking the steady state, right? So that's the steady state. So that's how this quantity m is defined. The position of the walker is given by this expression here. So you know, so this would be the position at time n. X0 would be the initial position. You can choose that to be 0. And yeah, it's then given as a sum of all of these y's, right? So at the first time, you choose from this set over here, you get a particular e value, and then you move in that direction. Then the next time value, you choose again, you get another e value, and then you move in that direction, and so on and so on. So good. Now, a key quantity for us would be this expression over here. So we've got xn minus the expectation value of xn, right? So you use the information that's on the slide. You can show that this expectation value is given by this n times m over here. Now, from this quantity, for any vector in our d-dimensional space, you can perform a decomposition, right? So you can decompose this random process here, right? This scalar product into a martingale, right? So this M here is a martingale, and some other contribution, right? Some other contribution, which eventually, so you can show based on what we've got, you know, it's some algebra, but it's not so hard to show, but you can show that this AN over here, you can show that this AN is actually, it's bounded independently of the parameter M, right? So then what is argued, especially in the original derivation for the central limit theorem, what's argued is that this process, this AN over here, it will not contribute at all to the central limit theorem, right? So you can show that it requires a little bit of algebra, but it's not too difficult. So the key quantity for us is this martingale over here, right? Now, what does this martingale look like? So again, you do a little bit of algebra and you find this expression for the martingale. I mean, the actual details of the expression is not super important. So this function f, it's defined over here. I've written this definition. And this quantity, you know, it involves this new matrix L, right? And L is it's a matrix, and it's a solution to this weird looking equation over here. So L minus, so this is the adjoint of our CPTP map, and it's given by this, it's equal to this kind of weird looking right-hand side, all right? So, but basically the key, you know, the key thing for us is that we're now working with this martingale M, right? You can show that this M does indeed satisfy the defining property of a martingale, right? So if you take delta M, right? So some sort of change in this martingale, some sort of change in this random process. If you take the expectation value of that, given some filtration, right, at n minus 1, you can show that this expectation value is 0. And how I think of this, how I at least think of this filtration is that, you know, given all the knowledge of all the events, right, so given all of the knowledge of all the past history of what this random process has done, that's sort of summarized by this filtration, right? So given all of the events that occurred up to time n minus 1, what's the expectation value of this incremental change in the martingale, right? So the defining property of a martingale is that this expectation value must be 0. And, you know, using this expression here, which is our martingale, you can show that it's exactly the case. So now, the nice thing about working with Markov chains and martingales is that there is, in the literature, there's a theorem. There's a central limit theorem that is applied for martingales, right? So basically the theorem says, if your martingale satisfies these two properties, these two equations, then your martingale essentially converges in distribution to a Gaussian with these parameters, right? So let's have a look at this. So, you know, if we want to think of maybe this first condition over here, this first equation, let's think about what we've got there. So this operator here, right? So this I is non-zero only when the conditions, you've got the absolute value of this delta mk is bigger than this quantity here. So epsilon times by the square root of n, right? So epsilon can be as small as you like. So as long as you have this condition, you've got the identity matrix here, right? So, and that's yeah, so this expectation value, the sum, this delta m squared is weighted by this, this operator here. So something that you can show, again, so given this expression, I mean, not super important to know what it looks like, but you can show that that delta m, right, is bounded. So what I've got here, delta mk, is bounded independently of k, right? So it's capped so the maximum value of this thing here is capped independently of k. So if we go back to what's happening here, so yeah, as we're doing the sum, so you can maybe think for small values of n, small values of k, for example, we can conceivably think of as this condition here being satisfied, and we start having non-zero contributions to the sum. But as n gets larger and larger, right, as k gets larger and larger, at some point this delta mk is going to reach its maximum, right, and that's not going to increase anymore. So as n then continues to increase, it's conceivable that we get to a point where this condition is no longer satisfied, right? So if this condition is no longer satisfied, that kind of kills off these higher, the contributions to this expression from, the high values of n, the large values of n. So what you've got is, something finite, some finite contribution divided by n, and we've got a limit as n goes to infinity. So I think it kind of makes sense that you get zero, right? So that's sort of, maybe a hand-waving argument or a heuristic argument as to why our martingale satisfies the first condition. And then again, it's a little bit of algebra, which it's a little bit exhausting to explain, but you basically use the definition of the martingale, and this ergodic theorem for the steady state. So the time average of a single trajectory converges to the steady state. You use all of this information, and you can show that our martingale satisfies the second equation, right? So so the only non-zero contribution to the left-hand side of that second condition is a finite condition, or is a finite quantity for all of these, for any vector L that you can choose. So what is that finite quantity? What is that contribution? Well, first of all, let me just note that it depends on mi. I'll show you the expression in a moment. It depends on this mi quantity, so also depends on this li, so those L operators, depends on the steady state, and of course the coin operators. So again, with some algebra, you can show that that right-hand side of the condition, right, of condition 2, equals this expression here, this arguably nice-looking expression, right? So again, so this expression for the covariance matrix, again, it depends on this quantity mi. So mi is given by that, right? This expression here. It's sort of like that m quantity that we defined originally, but now we just identify a particular axis, so sort of the mean value on a particular axis. This covariance matrix, it depends on the steady state. How do you get the steady state? Well, you solve this equation over here, right? So here's your CPTP map acting on rho infinity, and you can solve this equation to actually get your steady state. And these L operators, right? So here we've got Lj and Li. That comes from solving this weird looking thing over here, right? So in principle, so we've shown that our process, our random process that we began with, it satisfies the necessary conditions, right? The conditions set out for the central limit theorem. And by doing some fancy footwork, some fancy algebraic footwork, you can show that the covariance matrix is given by this expression here. And so basically, the coin operators you should have already. The steady state you can solve for. The m's we know how to find. The l's we also know how to find. Okay, so that is very good news for us. Now, so we have these nice analytic expressions, or these theoretically derived expressions that describes that describes this Gaussian distribution that we get from the central limit theorem. Can we subject it to some, at least some non-trivial checks, right? So in this 2015 paper for the microscopic walks, the microscopic derivation, Ilya and Francesco, they consider a one-dimensional example, right? They consider a one-dimensional example. Essentially, it's a two-level system, right? That's their walker, and it's on a circle. They define the coin operators to be this, right? So there's B, A, and C. And there's some conditions here or some definitions. So, you know, this expectation value of n, that's the mean number of photons, I guess, occupying a particular mode. This gamma over here, I think that's the coefficient of spontaneous emission. So again, that's, you know, property having to do with, I think, the bath. And yeah, just some more definitions. This parameter here, which is found in the A, that describes a weak external field in, you know, a particular direction. So taking that example and using our formula, right, our theoretical expressions, we can calculate what is the M, right? So using our expression here, our formulas, we can calculate what is the M. And, you know, after doing some mathematical crunching, you can find this expression here for the M, right? Again, after doing some mathematical crunching, you can find this expression here, this kind of complicated looking thing for the variance. Again, you know, so the actual knowing the actual expressions here, or what they look like, it's not so important. But what is important is that for the case that is considered in that work, in that calculation, these expressions, the M and the sigma squared, they agree completely. All right, so, you know, so for the case that they consider, the M and the sigma I showed in the formula reduce to the expressions that is listed in that paper. And just to, I guess, show you a nice picture, you can choose some, what probably is some reasonable values, right? So for the parameters in the problem, you can actually calculate some numbers for that mean and this variance, and you plot the normalized Gaussian distribution for that, right? So that's yeah, that was a nice example just to tell us that you know, we're going in the right direction. It seems that, you know, our central limit theorem is working. Now for that example that I showed you earlier on, that one-dimensional example, so this would be something like a numerical example. So here are those operators again, right? So here's the A0, the A1, the A2. You can solve for the steady state. So you act with your CPTP map on some unknown matrix, and you set it equal to, again, the same unknown matrix, and then you solve your equation. This is what you can find. Okay, and once you found your steady state, you can use those you can use those expressions to calculate the M. And for this example, we find an M of 0. So that was a nice, simple result. Now you can solve that weird-looking equation for the L, right? So let's go back. You can solve this equation here for this particular example. It boils down to solving this system of equations here, right? So here are the different entries for that L matrix, that 2x2 L matrix. So you solve the system, and we find that for our L. So now we're putting the pieces together, or we're gathering the pieces to actually calculate the variance, right? To calculate the sigma squared, or the C, like I've written here. So using that theoretical formula, right? So that theoretical formula, that analytic expression, plugging in all of the things that we found for the steady state and the L matrix and so on, we calculate a theoretical value to be equal to that. Okay, so that's what we've got. And then a nice thing to be able just to check is to, can we simulate the open quantum walk, and can we reproduce this number here, right? So that's summarized in this table here. So after, so this was done, I think, in the quantum trajectory formalism, or that procedure. So I've got data here for 10 steps for the open quantum walk, and then 100 steps, 1,000 steps, 10,000 steps, and 50,000 steps. And yeah, at least, you know, in this example, we can see some nice convergence happening here to the theoretical value. So again, our central limit theorem, it's sort of working, or it appears to work as expected. So that's good. I should also say that in the paper, we did look at some two-dimensional examples. You know, so I think it was a trapped ion system walking on a two-dimensional lattice. And we also compared theoretically predicted values for that covariance matrix. We compared that with the simulation of the open quantum walk. And again, we find very nice agreement with our, you know, our theoretically predicted values with the simulated values. Okay, so good. So that is about it. Let me try and conclude. So at least I've tried to convey the idea that there are interesting and important results for non-lazy open quantum walks, including now the central limit theorem. Now what we've done, or what we've discussed, is we formulated a homogeneous discrete time lazy OQW on a d-dimensional lattice, right? So we wrote that formalism down, and then using the quantum trajectories formalism, we were able to derive the central limit theorem, right, for such a model. Then, you know, we obtained some analytic expressions, you know, notably for the covariance matrix, right? And then lastly, we performed some non-trivial checks of our expression / model. And yeah, so that was basically a, you know, a summary of what we've been doing. Yeah, so I think, so let me stop here. I think I've spoken enough. Thank you for your attention. And yeah, then back to Francesco.
Yeah, Gary, thank you so much for the excellent talk. Ilya, are there questions for Gary?
I don't see any questions. We can maybe give a couple of minutes to our audience to formulate questions, and take into account that we don't have too many people. They can just raise their hand and we'll give them a chance to speak.
Perfect, thank you. So then maybe I can start asking a question to Gary. Gary, this is all very interesting, but how do you think that we can push this area of research forward? What immediate other questions arise from what you have shown? Or put it the other way around, are there any interesting fields of applications for the kind of central limit theorem that you have proven?
Yeah, so good question. So right now, I think for me, at least one thing that I can say is that one of the main assumptions that we made use of in this derivation was that the steady state was unique. Now, I guess it can be an interesting question as to what happens when you don't have that assumption. What happens if you relax that assumption? What happens if you have more than one steady state? And yeah, in that case, you know, what does the central limit theorem look like? You know, how does this affect our derivation? So I think that I have seen some papers which have tried to move in this direction. I don't think they've discussed the central limit theorem, but yeah, they do try and discuss what happens if you do have more than one steady state. How does an open quantum system behave, and so on and so on. At the moment, I'm still trying to understand those papers. So yeah, you know, hopefully at some point I'll have a good indication of what they do. But I think that's a nice starting point. You know, understanding some of those papers that those people have written, and then start thinking about, you know, how does this affect our central limit theorem? Because again, I think, yeah, all of those papers, or what's done before in sort of relaxing some of the assumptions that we've done. Again, that's, as far as I know, that is for non-lazy open quantum walks. So, you know, really proactive quantum walks who, you know, not lazy at all. So yeah, it'll be nice to try and understand what they've done, and yeah, try and generalize that to, again, the lazy case, because ultimately, as was shown in that microscopic derivation paper, any open quantum walk that is, you know, any microscopically derived open quantum walk necessarily must be lazy, right? It must have the self-jumping term. So yeah, there would be a nice generalization to sort of proceed with.
Okay, no, thank you very much, Gary. That I'm looking forward to that. Yeah, thank you. Ilya, I think there are questions coming up.
Yes, there is Camille wants to ask a question, and
yeah, hello, Gary. Thank you for this nice talk. I have kind of a bit of crazy question. Now, I was interested by the one comment you made at the beginning. So making a relation between open quantum, I think it was not open, between quantum walk and search algorithm. And I just had the idea that, I mean, it's I was looking at ants walking, and it looks, I don't know, but it looks like they're walking randomly, and so the question is I don't know if anybody already studied that, but it would be interesting to so maybe it's not in our field, it would be more with biologists or something like that, but to see if, for instance, ants or some other animals, when they're looking for, I don't know exactly what, maybe for food, or if they are doing a random walk, or another kind of random, maybe even quantum walk, why not? And so yeah, to maybe there's a relation between how an ant try to find what she's looking for, and I don't know, either the search algorithm or and to find out if, I don't know, maybe nature made that the ant follow the best algorithm to find something. I don't know. So it's, I mean, it's not exactly a question. It's more maybe a comment or something. I don't know.
Yeah. So yeah, no. Thank you for that. Thank you for that. So one thing that I maybe can say is that, yeah. So people do study this whole idea of quantum transport in biology. So there's some sort of biological systems and quantum transport. People do study. You know, there is some literature on that, and as far as I know, you know, for that, it's useful to have a framework for quantum walks in some kind of open environment. You know, so I guess where dissipation and decoherence and stuff like that, that's really playing quite a key role. So, I mean, maybe this could also encompass perhaps your ant, you know, looking for food or something like that. I mean, I don't know too much about these biological quantum transport models or these ideas. Yeah, and as for that search algorithm, so, I mean, it was a nice paper that I found. I just I wanted to try and look for an example where lazy quantum walks told us something interesting, something we might not have gotten, we might not have understood just by studying the, you know, the non-lazy walks, you know. And I came across I came across that paper. Yeah, so at least what's claimed by the author is that adding these self loops, maybe playing with the probability of the walker staying put actually does have some kind of impact on that search algorithm. Yeah, anything more than that, I'm not sure I could send you the reference if you like, but yeah, I pretty much know almost pretty much everything that I've spoken about. Everything that I've spoken about, that's pretty much all I know. So yeah, that's all I can say, I guess.
Okay, thank you very much. Yeah, so the link was between the search algorithm and lazy quantum walk. Yeah, okay.
Yeah. Yeah.
Okay. Now, but I think with ants, we can quite safely assume that they're rather classical, because I think it's quite well known that how they do the search, and they do search by just the chemical path creation. So I think it's, and all sorts of evolutionary algorithms are based on that. So I think it's rather classical object, while in some other instances it might be of interest. Okay, and we get a question from Graham, and I'm not sure whether Graham wants to talk or he just typed it and wants me to read the question. Graham, I'm just joining you, and if you want, you can read your question by yourself, or I can read it for you.
Hello, can you hear me?
I can hear you, yes.
Hi. Okay. I was just, so the question that I put into the, I'm not sure if you can read it, but the question that I put into the Q&A was that at one point in the talk you mentioned, I think you referenced a paper where, I think it's a paper from Ilya and Francesco, where they gave a microscopic derivation of an open quantum walk.
Yeah.
So as far as I can recall from that paper, under the appropriate approximations, the master equation that you can derive when you go from the discrete to a continuous time limit is of Limblad form, which kind of reflects the fact that in your open quantum walk, it's essentially a memoryless random process. But I was wondering that at the level of the Krauss map, if there's any obvious way of being able to add something that incorporates memory effects into the walk, if that makes sense.
I think it does make sense. And yeah, it's a good question. And I guess, yeah, the short answer is I don't know. Certainly if once you move over to this quantum trajectory formalism, you apply the map, you do a measurement, you apply the map, you do the measurement, you sort of, you do somehow, I guess, do away with any kind of memory. So, there you kind of do just get a nice Markov process. But yeah, just at the level of, doing the full OQW map, yeah, I'm not sure I can give a good answer to that. Yeah, maybe Ilya or Francesco can add some value.
Of course, one can consider some non-Markovian generalization, and if you just keep it, for example, within the Krauss form, so you just need to have like a Krauss apparatus which would be time dependent, and I think in that case, yeah, it's possible. But of course, it's also will hit the standard issue of what you call non-Markovian. But okay, that's a separate discussion. But like to have it like within a non-divisible map, which will have some sort of Krauss representation, I think that's rather plausible.
Okay, thanks.
Okay. Ilya, it seems there are no more questions. So Garry, thank you very much for the excellent talk. And we heard from the questions and comments, there are lots of open strengths that one can follow up and pursue, and probably lead to many more papers. Yeah. So we are really looking forward to that. and then we will invite you again to speak. Yeah. So Garry, thank you very much again for your time, and thank you to all the participants. And we will announce soon the next webinar, probably in 2 weeks' time or 3. Yeah. So thank you very much, everyone. Garry, thank you very much for your time and for the nice talk. Ilya, thank you for moderating the questions. Yeah. And we will see you soon again here in Zoom. Yeah. Thank you.
Thank you.
Bye.
Thank you. Thanks for
Bye. Bye.
Thank you. Bye. Thank
Bye.